Hi guys, this is Vicky, and today we're going to go through the 2005 Form B FRQ for AP Chemistry. I have been getting a lot of requests from a lot of the students that I tutor in regards to how to solve an acid-based question using an ICE table. And so I figured this would be a good review not only for those who are trying to take the AP exam, but for those who are trying to just get through a college Gen Chem class. Because the concept is exactly the same. So with no further ado, let's try doing this question. So number one, it says hypochlorous acid, HOCl, is a weak acid. And again, I always tell my students, if there is a Ka value, assume 100% that this is going to be a weak acid. Okay? Always, always, always. If there's a Kb value, it holds true for weak bases as well. Okay? So the question says it is a weak acid in water and K expression for HOCl is shown above. Write the chemical equation showing how HOCl behaves as an acid in water. So if you look at A, we know this is going to be products over reactants. So we know HOCl would actually have to be on the reactant side. And we know that this is going to go in water, right? And because this is a weak acid, um, we would use the arrow that goes back and forth, right? And let's look at the products. It's H3O plus OCl minus. Now, some students have asked me, how do you know when to put water and how do you know when not to put water? So a lot of times you do not put water when you're writing the net ionic equation. But if you're asked to write the full equation like they are right now, you do want to write it, okay? And that also means that you also want to symbolize that everything else is in aqueous except for water. Water would be pure liquid. Okay, cool. All right, let's continue with B. So B says calculate the pH of a 0.175 molarity solution of HOCl. So that means that I actually have HOCl and I'm actually going to get rid of the H2O just because I know that I don't really need it for this particular equation, for this particular problem, because I know that H2O is pure liquid and never partakes in a equilibrium equation. Okay, so here we go. We know that it's 0.175 molarity of HOCl that I start with, right? That means I don't have any products yet because this is at the very initial step of my chemical reaction. So what happens during the change? Some portion of HOCl will start to dissociate, and we know that it's going to be less than 5% because they told us that it's a weak acid. Okay, we also know that that particular stoichiometric amount of HOCl that's been dissociated is going to add on to the products. Okay, so again, we know that X is negligible because it's less than 5%, which means that 0.175 molarity of HOCl, X amount of H3O plus, and X amount of OCl minus are going to be produced. Now that I have this, now that I have all of the equilibrium amounts, concentrations of all the species in that particular solution, I can actually just plug it in into my Ka value. And it's going to be x times x over 0.175, right? And I know that my Ka value, because it has been given, is 3.2 times 10 to the negative 8. So if I solve for x, which happens to be the concentration of H plus, I can easily, I can easily find the pH. And so this is going to be the molarity of H plus concentration that I have. Now, how do I calculate pH? I just plug it in into this pH equation, which is negative log of H plus. And so I just plug that equation in there, and I end up with 4.13. So this is going to be my overall pH in this particular weak acid solution. Okay, all right, let's look at C. C says, write the net ionic equation for the reaction between the weak acid HOCl and a strong base of NaOH. So I know that I'm starting out with HOCl and I'm adding NaOH, and because this is an acid and that's a base, I know for a fact that I am going to be creating water and salt. Okay, and the salt is NaOCl. right? Okay. Now, they're asking us for a net ionic equation, and we know that sodium is super, 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 super soluble. So sodium, I can just take it out, right? So after I take that out, I end up with HOCl, okay, plus OH minus, yielding H2O plus OCl minus, right? Now remember, H2O, okay, in a neutralization reaction is a new product because this is the start of the reaction. We know that we have to create water in a neutralization reaction because that is the whole purpose of a neutralization reaction, right? So everything else now, because they all partook in the chemical reaction, they're all going to be in aqueous. Okay, so this right here would be my net ionic equation. Does that make sense? All right, let's continue with D. D says, okay, so let's do D1 first. So D1 says in an experiment, 20 milliliters of 0.175 molarity HOCl is placed in a flask and titrated with 6.55 milliliters of 0.435 molarity of NaOH. Okay, so this is basically just saying, okay, that I have some large amount of HOCl. Okay, I have some large amount of HOCl, and out of all of the HOCls that I have, okay, I am going to pour in a tiny amount of NaOH. Okay, so if I pour in a tiny amount of NaOH, the Na will split up and it'll probably like create a bond this way, and the OH minus will actually tear apart the proton from the HOCl and create H2O. Okay, so this is what they want you to calculate. So question number 1, they're telling you calculate the number of moles of NaOH added. So in order for you to find the number of moles, because obviously this is all given to you in molarity, which is concentration, and concentration is the same thing as kind of like grams, so you can't really figure out exactly how many head counts of NaOH and the head count of HOCl exists in that particular solution. So this is why we switch everything into moles before we do any type of calculation here. Okay, we need to figure out how many of these actually match up. So what is my mole of NaOH? So they told us that they have given us 0.435 molarity of it, and they have also given us 6.55 milliliters, which we know if we were to convert it, it's going to be 0.00655 liters. And we know that molarity times volume is going to give you moles. So this ends up being 2.85 moles, 2.85 times 10 to the negative 3 moles of OH minus. Okie dokies. So that is going to be your answer for 1. Let's continue to 2. So 2 says calculate the H3O plus concentration in the flask after NaOH has been added. So now we need to do 2 different types of ice tables. So first of all, we need to figure out, we know that we have a certain amount of HOCl, and we know we have a certain amount of OH minuses, and we know that we're not only creating OCl minuses, but we are also creating water, right? And that's liquid. Now, what is the moles of HOCl that I actually have? So I'm actually just going to figure that out, moles of HOCl. If you look, I had 20 milliliters, 0.175, so that's 0.175 molarity, and 20 milliliters, so it's that, right? And I end up with 0.0035 moles. So that's how many moles, okay, of HOCl I have, okay? And I have 0.00285 moles of OH minus. So which one is the limiting reactant? Obviously it's going to be OH minus. So OH minus is the strong one, so it's going to drive the whole reaction to the right, okay? Creating 0.00285 moles of OCl minus and 0.00285 moles of H2O. But again, we are not going to take under consideration H2O because that's pure liquid. Okay, so at the end of the day, okay, this buffer system, because it was a weak acid and its conjugate base, consumed up all of the OH minuses, and I end up with 0.00065 moles of HOCl, and I end up with 0.00285 moles of OCl minus. Again, these are moles. So then now I have to divide these by the total amount of volume. And we know that we had 6.55 milliliters from NaOH, and we also had 20 milliliters from HOCl. So that's going to be 26.55 milliliters, which ends up being 0.02655 liters, right? 0.02655 liters. And this is going to give me the new molarity of HOCl and OCl minus. So if you do the calculations, I end up with 0.0245 molarity of HOCl, and I end up with 0.107 molarity of OCl minus. So these are my new molarities. Now that I have my new molarities, I can actually go back and I can figure out how many HOCls actually naturally likes to dissociate in water. So I start out with 0.0245 molarities of that. I don't have any molarities of H+. I have artificially made this many molarities of OCl minus, X plus X plus X, and I end up with, obviously this is negligible, end up with 0.0245. This is my ice table. Okay. Oh, this is not negligible here. I'm sorry. Okay. Because we started out with 0, right? So then I have X amount of that, and I have 0.107 molarity of that. Now all I have to do is just plug it into my Ka value. And remember, the Ka value was given to us, right? Up there. So what is my Ka value from up here? And it was 3.2 times 10 to the negative 8. So all this is equal to 3.2 times 10 to the negative 8, and that's supposed to be X times 0.107 over 0.0245. And what is X? It is my concentration of H+, and I end up with 3.2 times 10 to the negative 8. So I end up with, if I do the calculations, I end up with 7.3 times 10 to the negative 9 molarity. Okie dokies? All right, last question. So the last question says, calculate the OH minus in the flask after NaOH. So the easiest way to do this is the KW equation, right? So if you guys remember, what is KW? KW is Ka times Kb. But KW is also concentration of H plus times concentration of OH minus, because this is the autoionization dissociation constant for water. So this is a constant, and we know it's 1 times 10 to the negative 14, which means it's 7.3 times 10 to the negative 9 times OH minus is equal to 1 times 10 to the negative 14. So what is my new concentration of OH minus? My new concentration of OH minus happens to be 1.4 times 10 to the negative 6 molarity. And that's your answer for that. And I hope this helped you guys understand a little bit about buffers and how to calculate buffers and how to calculate weak acids with strong bases interacting in a solution. If you guys like this, please give it a thumbs up. And if you guys have any other types of questions you guys want me to help you guys solve, please comment below. And I will see you guys next time. All right, bye.